Hello and welcome to High Voltage Engineering. We'll be talking about breakdown in solid dielectrics. In the previous class, we were talking about the introduction of the solid dielectrics, where we have discussed of different methods of breakdown. In this class, we'll be talking about the different methods in details. Okay, so first we'll be starting with the intrinsic breakdown. Now, what is this intrinsic breakdown? When voltages are applied only for short duration, that is the order of 10 to the power minus 8 seconds. The dielectric strength of the solid dielectric increases very rapidly to an upper limit called the intrinsic electric strength. Experimentally, this highest dielectric strength can be obtained only under best experimental conditions, when all extraneous influences have been isolated and the value depends only on the structure of the material and the temperature. The maximum electrical strength recorded is 15 megavolt per centimeter for polyvinyl alcohol at minus 196 degrees centigrade. The maximum strength usually obtained ranges from 5 megavolt centimeter to 10 megavolt centimeter. So intrinsic breakdown is basically a theoretical one. You do not get it in the practical sense because you cannot remove the other influences. So it is only when the short voltage is applied. So this is uh, the maximum insulation property that a solid can show, that is the intrinsic breakdown. So the intrinsic breakdown depends only upon the presence of free electrons which are capable of migrating through the lattice of the dielectric. Usually a small number of conduction electrons are present in the solid dielectrics along with some structural imperfection and small amount of impurities. The impurity atoms or molecules or both act as traps for the conduction electron up to certain ranges of electric field and temperatures. When this ranges exceeds, the addition of electrons to the trapped electrons are released, and these electrons participate in the conduction process. Based on this principle, two types of intrinsic breakdown mechanism have been proposed. So we have talked about the intrinsic breakdown mechanism. It is a basically the presence depends on the presence of free electrons that are capable of migrating through the lattice of the dielectric. So this breakdown is of the highest order. This is only possible to observe when there we can remove all the extraneous effects on the experiment and isolate the material, and then we can get this value. But in practical, this value is not obtained. So, uh, so we have talked about this. It is usually of a small number of conduction electrons are present in the solid dielectrics along with some structural imperfection and small amount of impurities. Okay, so uh, this impurity atom or molecules are both acts as trap for the conduction electron up to certain range of the electric temperature. When the ranges exceed, so these impurities actually they trap the electrons. But when a small amount of uh, electric field is applied, and if it goes to a range above that, they are not trapped and the electrons are released. These the intrinsic breakdown is just the measure of the amount of free electrons that are present in the material. Okay, so here we have talked about there are two types of breakdown, the electronic breakdown. One is the electronic intrinsic breakdown, one is the electronic breakdown. Okay, so under intrinsic breakdown we have this uh, electronic breakdown and the avalanche or streamer breakdown. Okay, so we have seen that based on the intrinsic breakdown, there are two types of intrinsic breakdown mechanism. So one is the electronic breakdown. The intrinsic breakdown occurs in time of the order of 10 to the power minus 8 seconds. Therefore, it is assumed that the electron it is to be electronic in nature. That is, it only depends on the electrons. The initial density of the conduction or the free electrons is also assumed to be large, and the electron-electron collision can occur. When an electric field is applied, the electron gain energy from the electric field and across the forbidden energy gap from the valence to the conduction band. When this process is repeated, more and more electron become available in the conduction band and eventually leads to a breakdown. So electrons were present in the valence band and they are trapped by the impurities. When slowly this uh, electric pulse is given, one by one this electron moves from the valence band to the conduction band. Okay, so when there are more number of electrons, free electrons for conduction, it creates a breakdown. Now we'll talk about the other theory, that is the streamer breakdown. Streamer breakdown is similarly to the we have seen in the streamer theory, where this breakdown occurs in gases in streams. The similar thing is there due to in for the solid. So this is a similar to breakdown of gases due to cumulative ionization. Conduction electron gain sufficient energy above a certain critical electric field and cause a liberation of electrons from the lattice atoms by collision. Under uniform field condition, if the electrodes are embedded in the specimen, breakdown will occur when an electron avalanche bridges the electrode gap. An electron within the dielectric starting from the cathode will drift towards the anode. During this motion, gains energy from the field and loses it during collision. When the energy is gained by an electron exceeds the lattice ionization potential, and additional electrons will be liberated due to the collision of the first electron. This process repeats itself resulting in the formation of electron avalanche. And the breakdown will occur when the avalanche exceeds a certain critical size. In practice, the breakdown does not occur by the formation of a single avalanche itself, but occurs as a result of many avalanches formed within the dielectric and extending step by step through the entire thickness of the material. This can be readily demonstrated in laboratory by applying an impulse voltage between point plane electrodes with a point embedded in a transparent solid dielectric such as perspex. So this is the streamer theory, where it is not when this avalanche takes place, it does not take place in a single line. There are multiple avalanches and these avalanches follow different paths. So it will create these streams of paths, and this is the avalanche or the streamer breakdown. Okay. Now we'll talk about the electromechanical breakdown. When solid dielectrics are subjected to high electric field, failure occurs due to electrostatic compressive forces which can exceed the mechanical compressive strength. So due to the electric field, the dielectric also gets compressed, and if it is beyond the mechanical stability, it will cause a failure. If the thickness of the specimen is D0 and is compressed to a thickness D under the applied voltage V, then electrically developed compressive strength is in equilibrium if this equation is valid, where y is the Young's modulus. Okay, so if we rearrange it, we can get to this value of v square equal to this expression. Okay, the mechanical instability occurs when this d by d0 is of this value of zero point 0.6, or in the inverse it is 1.67. Okay, so the highest apparent electric stress of breakdown is given by this expression. These are experimental expressions. Okay, you just need to remember these. Now recently this theory has been modified based on the concept of fracture mechanics. In the new mechanism, filamentary shaped cracks propagate through the dielectric material, releasing both electrostatic energy and electromechanical strain energy stored in the material due to the applied electric field. So in this, this is was the previous uh, equation that did govern this kind of mechanism, but recently we have some concept of the fracture mechanics, where uh, there are filamentary shaped cracks, okay, inside the insulators. There are thin cracks inside the insulator that propagate through the dielectric material, releasing both electrostatic energy as well as the mechanical energy. So both electrical and mechanical energy takes place in this mechanism. This is analogous to conventional mechanical crack propagation in brittle materials. So if you see brittle materials to be breaking, the creation of cracks, this is just something similar to that, whereby the cracks propagate spontaneously if the strain energy released is greater than the required is greater than that required to overcome the toughness of the material. Now we'll go to the thermal breakdown. So in the general, the breakdown voltage of solid dielectric should increase with its thickness, but this is true only up to a certain thickness, above which the heat generated in the dielectric due to the flow of current determines the conduction. When an electric field is applied to a dielectric, the conduction current, however small it may be, flows through the material. The current heats up and the specimen and the temperature rises. The heat generated is transferred to the surrounding medium by conduction through the solid dielectric and by radiation from the outer surfaces. Equilibrium is reached when the heat used to raise the temperature of the dielectric plus the heat radiated out equals to the heat generated. The heat generated under DC stress capital E is given by this equation. So here the breakdown we are talking about is due to the heat only. Okay, here we have sigma is the DC conductivity of the specimen. Okay, so under AC field, the heat generated is given by this equation in terms of watt per centimeter cube, where the F is the frequency in hertz, delta is the loss angle of the dielectric material, and capital E is the RMS value. The heat dissipated WT is given by this equation, where Cv is the specific heat of the specimen, T is the temperature of the specimen, K is the thermal conductivity of the specimen, and T is the time with which the heat is dissipated. Okay, so this is the equation you needed to keep in mind. So this is the heat dissipation in terms of the specific heat and the rate of the rise of temperature, and this divergence of K and gradient of T. So this is the equation. The equilibrium is reached when the heat generated, WdC or WAC, becomes equal to the heat dissipated. Okay, so when the heat generated and heat dissipated is equal, or WdC is equal to WT, and equilibrium is reached. In actual practice, there's always some heat that will be radiated out. You cannot have a particular equilibrium, and the breakdown occurs when only this generated heat in DC or in AC exceed the WT. Okay, so this causes a thermal breakdown. So this is the different type. We have discussed different types of breakdown mechanism of dielectrics in solids. So this is the end of the class. Thank you.